My goal in this video is to create a new function given a function that I know is continuous, and then tell you one of the most important things I can about that new function. So I'm told that f is a continuous function over a finite closed interval ab. So I could just imagine that f is this function. Right, I'm going to let this be y equals, and I'm going to choose the independent variable to be called t. And one of the things that's important here is it doesn't actually matter what I call that variable. I could call it t, I could call it x, I could call it q, I could call it the Batman symbol. And it wouldn't matter, right? Because I'm plugging in a number and getting out another real number, right? That's what functions do, and it's the only thing that really matters. So here I have y equals f of t. And this is how I want to define my new function. I'm going to call my new function big F of x. And I want it to be the integral from a to x of f of t dt. Okay, let's think about what that says. Whenever I plug in a value for x, I have to fill in the upper bound, and then I evaluate an integral. So I'm thinking about x as being some number on this interval where my function is continuous, and every time I plug in a value for x, I get out an area. So things we know about big F. If we plug in an x, we get out an area. Two, the independent variable is x. This variable t is not the independent variable, right? It's just kind of holding a place in my definite integral because I plug in an x, I evaluate the definite integral, and I get an area. And for that reason, the fact that calling that variable t doesn't really matter, we call t a dummy variable. So whatever t is, it doesn't matter, right? This is a t, that's a t, it's a question mark, that's a question mark, it's a q, that's a q, it's the Batman symbol, and that's the Batman symbol. It wouldn't matter, we'd get the same thing, because whenever we plug in an x, we're just getting an upper bound. All right, and then the fourth thing, I like to think about this function, big F, as a cumulative area function. Because whenever I plug in a value for x, I simply get the cumulative area, the net area between a and x. And even if my function looked a little different and had some negative values, maybe it looks something like this, I could still evaluate the definite integral between a and x. I would just, like in this example, clearly get a negative number. The amount of area that's below the x-axis is more than the amount of area above the x-axis, but I would still evaluate it and get a cumulative or net area. Okay, so I have this function big F, and here's something I want to tell you about big F that's super important. This statement is called the Fundamental Theorem of Calculus. Part 1. In a future video, we will talk about the Fundamental Theorem of Calculus Part 2, but the Fundamental Theorem Part 1 says, if f is continuous on a comma b, then this new function we've created, big F of x, is also continuous on that closed interval. It is differentiable on the open interval AB. And its derivative is big F prime of x is little f of x. Or in other words, if I differentiate this new function with respect to x, I get out little f of x. What this theorem says is this new function we've created is an antiderivative for little f. That if I give you a continuous function, this net area function is its antiderivative. Well, better said, is an antiderivative for that function. The Fundamental Theorem of Calculus Part 1 guarantees me that over an interval where a function is continuous, I am guaranteed to have an antiderivative, and I can build it just like that. In the next video, we're going to do some examples where we get to use the Fundamental Theorem of Calculus Part 1. After that, we're going to have 2 videos where we pick up enough information to be able to prove the Fundamental Theorem of Calculus Part 1.